You can stand up. You can do whatever you want. We'll work around you. Everybody, this is J.P. Lewis. I've known J.P. for a very long time, since back in Disney days. But you've been a fixture at Weta for a very long time, and now you're at C in Electronic Arts, right? And this hopefully will be one of 2 Chalk Talks. The second one, this one, there's no nothing. The next one is going to blow your mind, but I'm gonna keep that one under wraps. Just a teaser for that one. Curse of Dimensionality, which, holy smokes, if you've done any machine learning at all, by this curse. So take us home.
Okay. Do my
oh yeah, slide. I'm gonna. Thank you very much. You press a button. Select. Switch this over to that. Everything else will go away. Oh, actually, I can do this. Hold on. There. And then we press yellow to hide it. There you go.
Okay. So let's see. Most of my career I've been working in visual effects. These are some of the movies that I worked on, got a credit on, and also I'm sort of an academic groupie. I hang out at universities when I can. But this year I joined a research lab from Electronic Arts. A couple slides about seeds, focus areas, and the group of people. So it's going to be roughly 50 people, mostly in Stockholm, but we have branches here in Los Angeles and also in Montreal. Okay, so Curse of Dimensionality. First, I would like to talk just about what a dimension is. I'm self-taught mathematically, and I remember that dimension is something that I kind of struggled with. So in graphics, we deal with 3 dimensions, and so time is maybe 4 dimensions. What is 5 dimensions? So I'm going to guess that there's maybe a few people in the audience who are not super comfortable with what what do we mean when we say high dimensions, and why is this relevant? Something that used to confuse me is, so you have a one-dimensional function, takes one number as input, so this notation R1 is one real number as input goes to one real number as output. You draw the graph, and the graph lives on a 2-dimensional whiteboard, which is weird when you call it a one-dimensional function. And then if you have a 2-dimensional function, you can take 2 numbers as input, which might be latitude and longitude, and output a 3rd number, which could be height, and that could be a nice terrain model, a height field, but that lives in 3D. So kind of weird to me. So part of the resolution for myself was to stop using the terminology of one-dimensional function, 2-dimensional function, and instead it as m numbers come in, n numbers come out, and m and n can be any numbers you want. And so a good case is kind of the texture mapping correspondence where you have UV, 2 numbers come in, and X, Y, Z come out. So let's generalize this now. Take the example of an image. We think of an image as a 2-dimensional thing. But for me, the resolution of dimension is sort of anything that can change. And so imagine you have a megapixel black and white image. There's 1,000,000 pixels. Each one of them can change. So you can think of a megapixel image as having 1,000,000 dimensions. So a particular image then is a point in a 1,000,000-dimensional space. You can then apply this sort of standard geometric operations you might do in 3 dimensions, but generalized to 1,000,000 dimensions. Okay, so let's say you're and it's game industry, so it has very, very few vertices. It has 1,000 vertices. And each vertex is 3 dimensions. Each of the x, y, z of each vertex can change. So that's 3,000 numbers that can change. So you can say that a head model is a point in a 3,000 dimensional space. To make it more interesting, let's say that it's a blend shape head model, and this blend shape has 100 targets. In a sense, there's only 100 directions or 100 ways in which the head model can change. So what's really happening then is you have a 100-dimensional subspace, ambient space. Or you could say it's a 100-dimensional manifold. So manifold being like this, or you can think of it as sort of the generalization of a surface. A 100-dimensional generalized surface living in a 3,000-dimensional space. The point of this subspace is it constrains what can happen. So we said that a head is a point in 3,000 dimensions arbitrarily. You can't, if you just grab the x of one vertex and start dragging it, that gives you something like this that's no longer a reasonable face. What we would like for an excellent model would be that parameters that you can give to the artist, and with those parameters, the artist can make every possible reasonable configuration, but they can't make any non-models out of that. So that's, you can think of that maybe as a goal of most rigs, most parameterizations. That's, the blend shape models are an approximation of that. The kind of joint rig is an approximation, but neither of them really get you all the way there. And so in the case of a skeleton rig, it's possible to position the skeleton such that it interpenetrates. This model here I purchased from a Disney animator about 15 years ago. So this was as of 15 years ago. So his name is, to give credit, Hiroki Itazu. I'm sure from Los Angeles. 15 years ago, this was a state-of-the-art model. Here, what I did is take all the blend shape targets, excuse me, and so you see that not every gives you a reasonable face. So this thing that what the blend shape is trying to do is has kind of a word in machine learning, this manifold assumption that often your data set, even though it lives in high dimensions, the intrinsic or useful dimensionality of it is lower than the ambient dimension. Okay, and so let me pause here. So the point of the blend shape case is that you think of as 2D and 3D objects, but it is also useful to think of them as million-dimensional objects or 100-dimensional objects. So this is where the high dimensions come. You start thinking of this, you can then take existing algorithms and generalize them. So you have this square root of your x difference squared plus your y distance. 3D is dx squared plus dy squared plus dz squared square root. Coordinate, you can add a fifth coordinate, and you can construct a million-dimensional square difference, which is just your sum squared difference square root. And so this works as a measure of image distance, or as well you could consider the vector from the origin to your million-dimensional point, normalize that vector, and then take the angles between vectors, and that's a correlation between your images.
But this is only reasonable and like suitable, but not, is it meaningful?
Not necessarily, but sometimes. So template matching is an example where you take the angle between you take the correlation between your image template and the image that part of the image, and that, think of it in high dimensions, it's just the angle between the things. So sometimes, but not always.
Yeah.
But that's a good point. It brings up our topic. My statement of Curse of Dimensionality is that the algorithm may generalize, but our intuitions often do not. And so I'm going to give 5 or so examples of this. Machine learning algorithms require an amount of data that's exponential in the number of dimensions. And so an example of this, let's say you're fitting some data, and you're going to fit it with a spline curve, and you decided that if you have 10 points, that's good enough accuracy to fit your spline curve. As that to 2 dimensions, if 10 points is good enough in 1 dimension, then 100 points will be needed in 2 dimensions. Some points in 3 dimension, and this is rising exponentially. So by the time you get to 15 dimensions, that's going to require so much data that it's not going to fit on any computer. And it can get up to 100 dimensions. And we've already said 100 dimensions is a reasonable number for a blend shape model of data. If you need 10 points per dimension, that's more data than there are atoms in the universe. Our curse in that sense. Another version of it is this one. What we've got here, we're taking 1D, 2D, and 3D. Consider half of the volume. So in the 1D case, half of the volume is half of the line. In 2D, we're going to take half of the line in each dimension, but we've only got 1/4 of the volume now. In 3D, you've only got 1/8 of the volume. So hold that in mind, but now flip it around and keep the volume constant. So let's say you have some operation like you want to estimate a derivative, or in manifold learning, there's algorithms like local linear embedding where you need to get essentially a tangent plane, and you need some support for this tangent plane. You want to get in order to estimate what your tangent is. So let's say that you decide that to reliably estimate whatever it is you're looking for, your tangent or something, at least 1/10 of the, or let's say 1/100 of the total available data. 1/100 of the total available volume, assuming things are spread equally. Using this sort of picture up to many dimensions, and what happens is that the size of your support has to keep growing and growing to even get 1/100 of data. And so you get to this point where it has to encompass the whole volume even to get a fraction of your data. So you can't have locality and grab a number of points in high dimensions. Okay, statement number 2. Everything is near the surface. So to me, this figure sort of illustrates it. So what we've got is 2D and 3D, and which is in gray. And we're inscribing within that let's say it's size 0.95. And so the volume of the unit square, cube, hypercube is always going to be 1. So that's 1 raised to the power d. Of the hypercube is 0.95 raised to the power d. And if you say 0.95 to the 20th power in 20 dimensions, or 100th power, you're going to get a number that's very close to 0. The volume of this green thing goes to 0, even though its dimensions are almost the entire of the enclosing hypercube.
A question. So that's not the volume of the 0.95. It's the width at each dimension is.
Yeah. Did
So
I say it wrong?
I was assume the volume of 0.95 is still 0.95. 0.95 of the whole volume.
That's not the way to think of it.
Maybe maybe this I rewrote it I wrote it the wrong way.
Right.
If the width at each dimension is 0.95,
Yeah.
and you calculate that thing, it will become 0 at high dimension. But the volume of 0.95
If you say the volume is 0.95,
is still 0.95.
it's still 0.95.
Isn't the volume of a 0.95 units happen to you?
Yeah,
That's the way I read
Yeah.
it.
That's what I'm intending to say.
Okay.
So the slide's not clear. I apologize.
I don't understand it.
Sorry about that. So here, this is somebody's graph, somebody named Judd, to the credit of a cube, and you have a sphere that's exactly touching the faces of the cube, and plotting the of the sphere to the cube in different dimensions. So 1, 2, and so on. And so you can see by the time you get to 8 or 10 dimensions, the volume of the sphere, relatively speaking, is negligible. And then this is somebody's version trying to illustrate this. So this is not meant to be a realistic picture, but what's happening is that these corners of volume and the shrinks to 0. Okay, statement number 3. Everything is far away. So in this and the next one, like to think about kind of probing space by putting down randomly distributed points, but with a uniform distribution. So there's randomly chosen, they're concentrated in a particular place. So here, this plot is, I picked 1,000 numbers in various dimensions. So if it's a 40 random number, I choose 4 different random numbers, and the tuple of those makes your 4-dimensional random number, and so on. On the horizontal axis, it's plotting the dimension as we go from 1 up to 200. And so I picked the first random number that was generated, and then I searched through the remainder and asked what is the closest other point and what is the distance to that closest other point. And then plot that, and you can see that as the dimension goes up, the distance point gets further and further away. And so this has practical implications for spatial data structures. In fact, this actually came up with a former colleague of mine. Bit vectors were of a constant size and stuck them into a spatial data structure and was doing, what is the closest one to me lookup, and found that the objects were sort of in the furthest away bin, or maybe the furthest away 2 bits. So you can't use bins in space because of this.
If you use a log space, or like there's a lot of exponential going on there, and so if you're spacing
Yeah,
to cope with that dimension.
yeah.
Okay, cool.
So all directions are nearly perpendicular. This is getting weirder and weirder.
Yes.
Where, of course, when I read it, I believed it, but I wanted to check it out, so I wrote a little Python program and made this plot. And so this is generating, taking the angle between them, so normalizing them, take your dot product, and then take the inverse cosine of the dot product, and plot a histogram. And you can see it's concentrating about 1.57 or pi over 2 or 90 degrees. As your dimension increases, this plot continues to concentrate around that 90 degrees. Take those last 2 statements. So everything is far away, everything's equally far away, and everything is perpendicular. So in 3 dimensions, what would that mean? That would mean that all the randomly chosen points are on a lattice. which is kind of a contradictory statement. You choose random points that could live anywhere, and yet they end up on a lattice. So a little while working on this, and I felt like, okay, this is the moment in my life when I feel like maybe I'm living in the Matrix or something. But finally, I came up with this plot, and so it's not, but what I did here is generate triples of random points in high dimensions. Grab the first point and translate the whole space so that the first point is at the origin. Grab the second point and do a high dimensional rotate. So this was a householder transform to get the second point onto the horizontal axis. And then do one final rotate to get the third point into the, and this is what you get. And so the perpendicularity here, it doesn't show up in the plot because the perpendicularity is from the origin, is vectors from the origin to particular points. So you can kind of think of this as there's the origin and a vector to this point and a vector to that point. Those tend to be perpendicular. But anyway, so what this is saying is that when you choose random points in high dimensions, they live on a randomly rotated and translated lattice, which, yeah, I don't know what to make of that, but whether it's interesting or not. Anyway, okay, so Curse of Dimensionality. So now, last part of the talk, I'm going to switch to the Gaussian and how this potentially applies to things that we actually do. So here's our statement. The high dimensional Gaussian is also weird. So we think of the Gaussian as this thing where it's concentrated near the origin and it falls off quite rapidly. In high dimensions, the Gaussian is a heavy-tailed distribution. So here what I've done is make this plot where this is, again, the dimension on the horizontal, and on the vertical, this is a hyperspherically symmetric Gaussian. I'm plotting the amount of probability that is out of the unit. And so at dimension 1, this is the complement of this thing here. There's a rule in statistics which is 66, 95, 99.7, I think. But this is the complement of the 66% of your probability that lies within one standard deviation. But then as you go up, the amount of probability volume outside your unit hyperball continues to grow, and you can see already by 10 dimensions it's flattened off. I did this in Mathematica, and I asked for numeric evaluation at 100 dimensions, and it gave back 1. And so I'm assuming Mathematica probably uses 64-bit, so it doubles. But it didn't say 0.9999 something, it said 1. Yeah, all of the probability volume is concentrated in the tail. And this figure kind of shows it to me. So this is an attempt at making a cartoon Gaussian where some radius, whether it's unit or whatever, in tan here, and this is in 1 dimension. And if you consider the ratio of the tan to the blue in 1 dimension versus 2 dimension, you can see that there's much more blue in the 2 dimension, and that continues to grow, although it is offset by the fact that the Gaussian is causing it to fall away quickly. Here, this is the same kind of thing where we're radially integrating around the hyper-Gaussian, showing the radially integrated probability mass, and it concentrates in this kind of shell in high dimensions. High-dimensional Gaussian is this weird thing where there's no probability in the center, even though the single highest probability point is in the center. A paradox. There's a high probability point in the center, but if you were to sample from it, you would never get that point. because the probability mass is around the outside. Maybe think of it as, you've got this sort of high point in the center. It's overwhelmingly balanced by the fact that there's this super broad area of very low level stuff that it's so broad that all the probability processing. There's this thing, the Dirac delta, which is it's sort of a function. Strictly speaking, it's more like a construct. It's a generalized function. It's this thing that's infinitely thin, all such that when you integrate over it, you get one. The high dimensional Gaussian is almost like the flip of this. So the Dirac delta, its width is 0, its integral is 1. The high dimensional Gaussian, its width is not 0, but when you integrate over it, it's effectively 0 or almost 0. Okay, so this slide title, so it doesn't matter. So think of faces as points in 100 dimensions and various estimates that, 100 dimensions are kind of a ballpark for film work and also for some academic investigations. People use linear PCA models that have an associated Gaussian assumption. Let me talk about that in a second. But so examples are in this paper in 1999, I think, or in the computer vision side, active appearance models, as well as comes up in psychology. People have proposed that there is a Gaussian model of facial proportions and so on. PCA doesn't strictly require assuming Gaussian data, but two statements about it. One is that the thing that's captured in PCA is a covariance, and that uniquely specifies a Gaussian. It does not give you detail to say anything more than that. That's the other thing I should say. I forget, so I'll go on. There was another point. So when people are working with these models, they often do a couple things that assume Gaussianness. And so one example is your regularization, where you have your PCA coefficients, and you put a regularizer on them that is trying to push them towards 0. 0 the center of this Gaussian where there's no mass. A second thing is this procedure, so maximum a posteriori, where this will come up where you want to, for example, have some partial constraints on something and then find a most probable model that satisfies those constraints. So you can think of maybe you've got some mocap markers on a face, but maybe only half the face is visible, and you want to estimate where the other mocap markers ought to be. So in this procedure, you specify a prior probability, and sort of most of the time, it's not required, but most of the time people pick a Gaussian, and one reason for that is it's called the prior very nicely. And then you apply Bayes' theorem here, and you can get your most probable model, a distribution, in fact, over models. But in the MAP procedure, pick the maximum of your posterior as the model you should use. So here's a visual of that. So here, the black curve is your prior. So it's this broad diffuse thing where you're saying, well, I think it's around here, but I'm not super sure. Curve is your likelihood. So that's what happens after you measured your data. And then the red is your posterior. And the MAP procedure says we are going to pick that posterior. So that procedure, I'm going to argue, is wrong in high dimensions, even though it has been applied in graphics and vision in this way. So this is a cartoon plot. Don't take it too literally. That's why it says this one. But right here, the gray stuff is our hyper ellipsoidal shell where all the probability lies. Our constraint. drawn the Gaussian profile there, find somewhere this constraint line, we want to find model to use. And MAP says we're going to pick the point there that is closest to the actually. And so we're picking a point where there's no probability. So this is kind of in contradiction to this work in psychology. So in going through these thoughts, I thought, okay, well, possibly be right. Surely people have talked about this. And so I looked into some machine learning books, and most of them do talk about Curse of Dimensionality, but they don't actually say anything about applying map and how map relates to the curse. This example here. And one, David Mackay, and so he has this to say. So now here's example of this. So this is the parents model. Code was written by Zhenyao Mo when he was a student at USC. What I'm doing here is interpolating from the face on the left to the face on the right. So both rows have the same right. And in one case, I'm the hypervolume, so that's the one on the top, and in the bottom case, I'm sticking to the, I'm going from one to the other, but sticking to the high probability area. See what happens when you cut across the top, you get this sort of airbrush that doesn't have any detail to them. Sample and the zoom in, and once again, you get sort of Mr. Airbrushed on the top. And then here's a couple movies. Airbrushed on the left, probability on the right. So play that one again. And then this one was a weird one for me. So the movie's playing. When I watch it, I don't really see much happening, but when you scrub it, you can see that's changing quite a bit. So this is one of these change blindness things where you can't see it while it's happening. It happens slowly enough. Yeah,
That's weird.
Off topic, but I have enough time. Yeah, I watched this change blindness video that was compiled by psychologists, and there was a couple of these where you saw this picture of a Mediterranean city, and it says look at the city and spot what changes, and you stare at it for 2 minutes, you don't see a single thing. You play it back, and everything has changed. Yeah.
Wow.
Yeah, so that's. I think
Sorry,
that's
what are you mentioned that there's a difference between the two. I just didn't catch.
Yeah. See, because
yeah, okay.
I totally missed it. Yeah.
So we're going from one face to another, and the guy on the left is cutting across the hypervolume, and the guy on the right is sticking to high probability. So, this example, I guess these two people were closer together. So in pictures, it's sort of the first example was maybe here and here, but these two guys are maybe here and here, so there's not that much. So that's a talk. Actually, one more point on this. So this brings up the issue of there's when you look at the deep learning papers, there's a lot of examples where you're interpolating in your latent space, and so this is pointing out that to do so, you should believe that your network has space into something where it's reasonable to do linear interpolation. And on the one hand, a deep network has more chances of doing that than a linear model. But on the other hand, there are some, for example, the BAE, where your latent space is explicitly regularized to And so then, maybe it's not the right thing to do. And so knowing this, when I see some of the interpolations, sometimes you see your beautiful face image, and then it does some weird stuff, and then you see another one, and it has sort of this rhythm to it. What's happening.
Nobody has airbrush face. So when
Yeah.
you are doing the,
Well,
nobody actually have those airbrush faces. I mean, because you're right, they look wrong.
I'm not arguing that, but I guess I would argue that from this, if you assume Gaussian distributions, and nobody has that.
It'll be interesting to actually validate it.
Yeah. So this is wrapping up the content of this talk is mostly in this paper from this conference, Mathematics Mice, it's called, Mathematics. And
So, but what's the takeaway from this? What do we have to change our algorithms? Do we have to, or are we just doomed to, we put in distance and wrongness, or?
you're all doomed.
Yeah.
There's no hope.
Yeah. And then why doesn't machine learning actually work? Because it does work, and you're bopping around in this monstrous space.
The answer.
Well, yeah, that's a good point. But
I mean,
maybe people would say it works for two reasons. One is the manifold assumption that your data is actually lower dimensional than the actual image.
exactly right. Yeah.
Quite a bit. And then as well, there was a, did you say Baidu, the Chinese?
I do.
Baidu? From them, where they were plotting this amount of data that you need. It really does need a lot more data to get even small improvements.
Yeah. When I do back propagation, Oregon, a very small number at the end, the loss function of my learning often comes down to a small value if I'm classifying something, or if maybe it's the image itself. I'm doing what you're doing. I'm taking two images, I'm subtracting to each other and producing a single number that says that this image is different than the image that I actually want. And so then I take that and I back propagate it into this monstrously dimensional thing. Small little changes to this net that has dimensions or so.
And you're super vulnerable to overfitting.
Vulnerable to a lot of stuff, right? And yet it still works. It's working. It's totally working, right?
I think J.P. was saying is that very high dimensional, your loss function is always very high because everything is.
Exactly, right.
That's what you said.
Yeah,
That's why you're doing.
yeah, that's why we're due. And yet, because it is a curse, right? But
Yeah, I mean, I guess if you start to get close enough, your thing is going to become a better approximation.
Right. Yes. Once the data becomes clustered, then yeah, then it becomes possible. Okay. Key thing that you mentioned right off the bat was that it goes against intuition. Intuition in 3 dimensions, and it's like, oh, everything's fine. But once you start thinking about things in a million dimensions,
Yeah, or even 20.
or even 20, right?
And so this comes up, like you can find cigarette papers from where people were using MAP on body models that had 50 50 degrees of freedom on them and stuff. So it works, yeah. But it works. The guy on the left, see the guy on the right. You might say that the guy on the left
Was okay.
was okay.
Yeah.
Yeah. Maybe this is just saying we can, if we can find a way to make use of this, we can improve things. Yeah. That's all.
How did you make this work computationally to stay over the Gaussian band?
So I interpolated across, but then pushed it appropriate for the band. So in other words, going across here, but then at each point pushing it up like that. Probably more. I apologize, I did this several years ago, but probably more likely like pushing it in the radial direction.
If network in autoencoders also does that, or does it not?
Yeah, that's a question I have. Like, to what extent does an autoencoder successfully kind of flatten your space sort of thing? Do just as you would. And so in the VAE case, I would think.
So the takeaway from this is, well, we're not all doomed, but when you walk into dimensions, one does not simply walk into higher dimensions. You have to be very careful about it.
Or truly high dimension.
Yeah. But this also, I mean, gone through this. We've had problems interpolating rings, right? And you can interpolate rings with degree of freedom fairly easily, but as you start 7 degrees of freedom and stuff like that, you can easily, you are doing a 7-dimensional space, and you have to be very, very careful about it.
Had a former colleague, Peter Hillman, who had an intuition for, or a way of saying why you can reasonably think that everything is far away in high dimensions. So 100 dimensions, if 2 points are going to be close, every single one of those 100 numbers has to be each other. But to be far away, all it takes is one of those 100 to be different. And so somebody else told me that way to think of things is that in high dimensions, if you have a manifold, there's so many more directions that manifold can wiggle. And that's a problem that's a big problem for regression. In that,
Oh, right, yeah.
So is it the case that the only way we can really get the result or walking around in a high dimensional space is possible only if we have an understanding of what the constraint manifold should be? Because I mean, if I wanted to interpolate in a high dimensional space, the only brute force approach for me at start is line connects them, manifold, and a very good understanding of what these domains are that I'm representing. Would that solve the solution for it, or?
So I'm not sure, but I think it. This was talking about the Gaussian, but there's, going back to the previous, that all in high dimensional spaces in general, all of the volume is on the outside. Even if you don't believe that it's Gaussian, you could still take that statement that all the volume is towards the outside and design your algorithm to make use of that somehow. Center. That's our takeaway. Avoid the center.
Yeah, okay.
There's nothing there.
Well, this was inspiring. Thank you very much, JP. Brilliant. Thank you. All right. Next week, I have no idea what the Chalk Talk will be on.
I feel like this is to either a public lecture or maybe just watch a YouTube video that talked about like the stelliferous end at another one of these talks where like
Yep.
there's no meaning to it.
Exactly. All right. Thank you, guys. See you next week. And then there will be no Chalk Talk over the Christmas holidays because, come on.